Let's go through the midterm exam problems. The first question is about the training error and test error and irreducible error. So both graph has some long point. Okay, so we have to correct something from the two graphs. First of all, what is the problem for graph A? Essentially, the meaning of irreducible error is observation error. So the test error must be greater than or equal to the irreducible error. So this part, training error below the irreducible error, is wrong. So either this graph move to up to above the irreducible error bar, or we have to move this dot line to the below of training error curve. What is the long point of graph B? In general, the training error is below the test error because we look at the training data point when we find the good parameters for your model. Basically, at that time, we solve the minimization problem with the objective function error, training error, right? So generally, training error is below the test error because test error is the error for a new observation. The second question is about the linear regression versus polynomial regression. So here, basically, when you use linear regression, the number of parameters this is just 2. But when you use polynomial regression with degree 4, then the number of parameters is 5. Naturally, when you increase the number of parameters, you can expect a better training error, right? So in terms of the training error, the polynomial degree regression is better than the simple linear regression. This is polynomial. But in terms of the test error, since the original model, the ground truth model, is simple linear model, when you increase the number of parameters and when you increase the flexibility of your model with increased number of parameters, which just decrease the training error, but it also increased the overfitting issue. It just overfit your training data. So in terms of test error, it is very highly likely your test error with polynomial regression will be much bigger than the test error with simple linear regression. So this is just simple linear regression is the better one. Okay, the third question is the cross-validation strategy. Essentially, this is very important when you train something with your own data set. So when you have training data or when you have some data set, and if you want to verify several different models using your own training process, you have to separate your training data into 2 different parts at the beginning as training data and test data, and you never use test data for your any training process. So even for the first part, screen the predictors, you cannot use the test data point. So if you find a subset of good predictors that show fairly strong correlation with the class label for your entire dataset, this already observes something of your test dataset, so which break the cross-validation concept. Okay. So this is not the correct process of your cross-validation. The first question is about the LDA and QDA. The first one, how can we obtain the LDA, linear discriminant function, when every covariance matrix equal to the same covariant matrix big sigma for all k, then the discriminant function becomes linear. On the other hand, if the covariance matrix is not the same but its own covariance matrix, so sigma k is not equal to sigma k prime when k is not equal to k prime, then the discriminant function is not linear. Very simple, right? The fifth question is about logistic regression definition. What is the logistic regression? So logistic regression is some kind of it's a very simple classification algorithm using logistic function, and logistic function is very simple, exponential x over 1 plus exponential x, and the beauty of the logistic function is the output of logistic function always between 0 and 1. When x go to infinity, this value is equal to 1. When x go to minus infinity, this value is equal to 0. So fx is like a probability value. The probability value for any event must be inside 0 and 1 interval. And logistic function can guarantee the output range between 0 and 1. So it is very nice function for describing some probability of your event. So how can we obtain the parameters in the logistic function? So essentially in the logistic regression, we use the very simple linear function beta 0 plus beta 1 x as the logit value. And then we train the logistic function using likelihood function maximization problem. So we maximize beta 0 and beta 1 that having the largest log likelihood value from your training data. Okay, so using the training data, you basically maximize the log likelihood value by controlling the parameter beta 0 and beta 1. Okay, next question is why we have to introduce dummy variables to deal with qualitative predictors. So essentially, this is also very important when you have such a classical input values. And if you assign a random or some values to each class index, then you can convert the qualitative predictors to quantitative predictors. But the problem of this kind of conversion is when you assign number, then the output has some pattern, and the pattern usually you don't want. So for instance, in this case, when FB is greater than FC, then which naturally imply FC greater than or equal to FA from the definition of ABC, right? And FB minus FA is equal to FC minus FB. So there is some relationship comes up with the definition of or your assignment of the number to each class. Okay, so this is sometimes really bad, usually really bad. And to escape this very critical issue, we have to introduce dummy variables. Next question is, what is the likelihood function for the data set with this posterior probability? The likelihood, the main assumption is each observation is independent, and the probability of independent event is just product of each event probability. So this is product I from 1 to n, probability y is equal to yi for given xi, and this is you can compute very easily, right? This is 1 over sigma square root of 2 pi per to n exponential minus 1 over sigma square summation I1 to n yi minus beta 0 minus beta 1 x square. Okay, so it's kind of 1 over sigma square root of 2 pi per to n exponential minus 1 over sigma square RSS value. So from this is very interesting. Maximizing the likelihood function is equal to minimizing the RSS value of your linear regression. Okay, so using this kind of posterior concept, you can convert the original linear regression problem to this likelihood maximization problem. So there is connection. Essentially, the linear regression, the main assumption was the observation error is IID Gaussian, and essentially the IID Gaussian assumption make this likelihood function, and this likelihood function makes such RSS minimization problem. Okay. The next question is, we have a data set x1, y1, x2, y2 up to xn, yn. What is the probability for the event that x1, y1 belongs to a bootstrap data? So what is bootstrapping? Bootstrapping means at each time we make random sampling with replacements, which means at each time this particular data is selected with probability 1 over n. Okay, so this data point will belong to a bootstrap data set at the first round with probability 1 over n, and will not belong to the bootstrap dataset with probability 1 over n. So the probability x1, y1 does not belong to a bootstrap dataset is 1 over n part n. This is the probability this particular data point does not belong to a bootstrap dataset, which is approximately 1 over e. So the probability for the event that x1, y1 belongs to a bootstrap dataset is 1 over n part n. Roughly, this value is equal to 1 over e. Okay. Next question. There are two lasso algorithms where x bar is equal to this. Then show that the both algorithms find the same beta 1 up to beta p. So here the important point is this additional cost function which define the lasso algorithm does not depend on beta 0. Beta 0 does not change these two additional cost functions. So you can very freely control beta 0 value. For this minimization process, you can very freely control beta 0 so that this RSS value can be minimized. On the other hand, if you control beta 1 through beta p, you have to take into account both this RSS part and the additional cost part so that your total loss function can be minimized. In this sense, so this x bar times beta z can be cancelled out with a new definition of beta 0. Okay, so this additional constant, essentially you can control this additional constant using new beta 0. Okay, more precisely, when you change beta 0 to beta 0 minus summation j1 to p x bar j beta z to new beta z, basically you have the same loss value. So you can have the same solution for beta 1 to beta p. Okay. Next question. Suppose that y blah blah blah. So here I want to say sorry. This is not max. This is min. Okay. So why this is the same? So this posterior property is equal to, from the base rule, property of x1 through xn, y1 through yn, property x1 through xn, y1 through yn, given beta 1 through beta p. Right? Okay. And this is argmax. And this is constant. In the optimization process, when you multiply some constant value, which does not change the solution, you can very freely multiply any constant as you want, which does not change this argmax process. So we can simply ignore this denominator because this is just constant. We only have this one, so we want to find argmax of this conditional distribution. And from the assumption, we know that each observation, each data set x1, y1, x2, y2, and so on, they are independent. So we can rewrite this conditional distribution as product of property x1, y1, xi, yi, I from 1 to n for given beta 1 to beta p. Okay. And from the assumptions, this is equal to what? Oh, sorry, we have to multiply 40 beta 1 through beta p as well. Okay. Okay, and this part is equals to this, and from the definition, we have this IID and this observation. So this is product I1 to n exponential 1 over sigma 2 pi n exponential minus yi minus beta sorry, beta z xij square. And this part, probability beta 1 through beta p, this is because we assume that this, right? So this is equal to product of probability beta j from 1 to p. Okay, good. And we want to make this one again. Since this is just constant, we can simply ignore this part for this argmax process, right? And exponential function is monotonically increasing function. So argmax of some exponential function is equal to argmax of this logic value. Right? So then this is equal to this. Argmax this is equal to argmax summation minus yi minus sum of beta z xij square plus sum here j, this is I, j ln probability beta j. Okay, so the remaining thing is find this property so that this is equal to this. That's it. Oh, sorry, I forgot the sigma square here. So there is sigma square. There as well. Right. So please try yourself to finish the solution. It's not too difficult, and if you cannot finish this, then please feel free to ask questions to TAs or using Q&A board or classroom board. Okay. The last question is, to perform best stepwise selection, how many models do we have to test? How many models do we have to test for stepwise selection? Okay, so this question is very sorry. Simple. To do best subset selection, you have to test all the subsets of your predictors. So which means the number of subset of p element, and you have to test 2 to the p number of models for the best subset selections. But for the first stepwise selection, which is difficult, which is different, you just incrementally test your model. So at the first, you just test the empty set, and you test the p different single predictor simple linear regression. And using the one best single predictor model, you incrementally add one more predictor. So where you have to test p-1 model, and then you have to test p-2 model up to the last case. So the number of all the models you have to test is 1 plus p minus 1 plus p minus 2 plus up and so on, and which is p plus 1 over 2 plus 1 different models you have to test for the fourth stepwise selection. And if you manipulate some stopping rule, you can test less than p times p plus 1 over 2 plus 1 models, because you can stop at some point before it reaches to one model case. Okay, whole model case. Alright, so I briefly explain how to solve the midterm exam, and which is very important concepts, which are very important concepts. So I hope all you guys can solve all these questions yourself without help of other guys, because these concepts are very key to understand other machine learning algorithms and the remaining chapters of this book for the remaining semester.